a square, you can write and read one symbol, let's say, from some alphabet. Okay, so that's the storage medium of the Turing machine. It's a tape, not a stack. Okay, a stack's too limited. A stack, by definition, you can only use it in a LIFO or FILO manner, you know, last in, first out, or FILO, first in, last out manner. Whereas the tape can be read and written to. You know, you can read or write a symbol on each square, and the device that does the reading and writing, you could call that a head, H-E-A-D, like a read-write head. Okay, and that head can move from square to square. It can move left or it can move right to the neighbouring square from where it was. Okay, so that's sort of the guts of the mechanics of the Turing machine. And so a Turing machine will have its current state, just the way a finite automaton does. Okay, it can be reading the symbol on its current square. So let's say I have 5 squares here. Let's say the head, the read-write head, is positioned at the middle square, and it reads what the symbol is there, and depending on what that symbol is and its current state, it will then do something. And the choice of the something that it does, like the next step, whatever it is, that will depend on the transition function. So Turing machines have transition functions. So you know, there's a lot that's similar to what you're used to from the previous 2 chapters on the previous 2 models. The first model, the finite automaton, and the second model, the PDA, push-down automaton. Okay, right. So now, what's really amazing about the Turing machine, the TM, it's a much more accurate model of the general purpose, you know, programmable computer that we have today. You know, computer in the usual sense of the word, you know, some machine that calculates. Okay, now a TM can do anything a real computer can do. Now that essentially is, you know, the ChurchTuringThesis. You know, it's essentially an article of faith. You can't really prove it. No one's proved it. But on the other hand, everyone believes it, and nobody has disproved it. Okay. So anything a machine, a computer can do, even today's supercomputers, you know, with 10 to the power 16 operations per second. You know, like 10 quadrillion, trillion is 10 to the 12, quintillion, quadrillion, yeah, quadrillion, that's 4, trillion is 3, billion by is 2, yeah, so 10 quadrillion calculations a second, state-of-the-art supercomputers today. Anything they can do, a Turing machine can also do. Hugely less quickly, of course, but in principle can still do. They have equal power, okay? Meaning they can do the same set of tasks. All right. Okay, so Church and Turing, two guys, two mathematical logicians. Although Turing was more a mathematician, he had many talents. He was a polymath in the full sense of the term. Many branches of math he was interested in. He pioneered the mathematics of pattern formation, as in embryogenesis, stuff like that. He was the father of artificial intelligence. You know, that was his vision, that machines could be intelligent. He invented the Turing test in artificial intelligence. Like, how do you know when a machine is intelligent? Well, when it can converse with you just at the same level as a human being, essentially. That's the Turing test. What else? Well, the modern father of the general purpose programmable computer, right? Yeah, guy's just amazing. And the fucking British government killed the bastard. That's the Aussie in me talking. Okay. Church was more strictly a mathematical logician, also fascinated by Hilbert's challenge to find mechanical procedures that would allow you to automatically deduce theorems from a set of axioms. And I think he was the very first to show that there were certain type of problems that could not be computed. And pretty quickly Turing came out with his famous halting problem soon after. So Church and Turing sort of, and yeah, there are a few others along the same lines as Church, the American mathematical logician. Kleene, K-L-E-E-N-E is another one, and Post, P-O-S-T. So you talk about post machines. Okay, so essentially the ChurchTuringThesis says that any computer can do, anything that's computable can be computed by a Turing machine. That's sort of the essence of it. We'll go into, just giving you an overview. We'll do the details later. All right. Okay, so a TM can do anything a real computer can do, and I put 3 exclamation marks there because that it's a major statement. Okay, and our whole modern lifestyle that we all live effectively is based on this, right? We can get computers to do virtually anything, and that's a common myth. People tend to think a computer can do anything. No. A very big no, that's not the case. However, even a TM cannot solve certain problems. There are some problems that are just theoretically unsolvable, provably unsolvable, which is interesting. It's fascinating. And we will meet our first one next chapter. And since this is a fairly short chapter, fairly soon, we will come across the famous halting problem of Turing, one of the landmarks, one of the pillars of the theory of computation in the 20th century. It's one of the real biggies, and we'll do it soon. The halting problem. All right. So such problems, like for example, the halting problem, they're beyond the theoretical limit of what computers can do. They're outside theoretically possible computation. Just cannot be done, and you can prove. Mathematically, rigorous proof that certain tasks, like the halting problem, cannot be done, cannot be solved, unsolvable. Okay, all right. So now we start getting into the guts of the description of the Turing machine. It has an infinite tape, as I was with the toilet paper. So that's its memory. Okay, so you can read and write on the tape. So if you can write on the tape, well, then read it back later. That's your memory, and it's an infinite tape, so you have infinite memory storage on a TM, a Turing machine. Okay, and it has a tape head. That's the device. Just imagine some mechanical device, and it can read and write onto a square. So a tape is just a sequence of squares. Just like toilet paper. It's divided into squares, segmented or perforated. Into squares of your tape. Okay, so the tape head or the read-write head, it's usually called the read-write head. So the tape head can read and write symbols, let's say 1 symbol per square, keep it simple. Can read or write 1 symbol per square on the tape. Okay, and the tape is of infinite extent. It can go infinitely to the left or the right, usually. I mean, there are variations, right? It might be finite one way. There might be an end of the tape, like on this side, and infinitely long that side. I think they're equivalent. So there are variations of Turing machines, and in fact that's the topic of section 2. You might have a machine, a TM, with say 2 tapes or n tapes or whatever. Okay, like here's your tape. And let's say the pen here is your read-write head. Well, that tape, the read-write head can move. right? It can move left 1 square, move right 1 square. Well, it keeps doing that. It can move anywhere in the tape. Now, equivalently, because it's all relative, right? You could keep the head fixed, and you could have the tape moving. Effectively the same. Okay. So a Turing machine, its mechanics, it read and writes symbols onto and from the tape. Let's say one symbol per square on the tape. And the transition function for that machine, that TM, will depend on what? Its current state, the symbol that it's reading at the moment, when the read-write head on the square that it's currently reading. So those two inputs, those two parameters go in, current state and the symbol it's currently reading, and as output there'll be three parameters as the output, as the next step, okay? The next state, okay? Just like a finite automaton. What it writes, it may write a symbol onto the same position, the same square. In other words, it would overwrite the symbol that was there. In other words, the symbol that it read. Okay, that's the second thing. So the write symbol. And the third thing is, does it move 1 square to the left or to the right? Now, if you think about it, it doesn't make any sense to just stay where it is. That would be redundant. It's just inefficient. So you just your next move, literally, of the read-write head is you move to 1 square to the left or to the right, and you indicate that by just 2 letters, L or R, left or right. Okay. So that's a sort of an overview, and then well, next session we'll get a bit more details.